Wave propagation, space waves, part 1, series on antennas and wave propagation, lecture number 6.17. Wave takes the form of space wave and travels in straight lines when its frequency is above HF band. Microwave communication systems use widely space waves for their functioning. Space waves usually travel in troposphere as space wave based communication links are established near the surface of the earth. Hence, for space waves, medium is troposphere, which is lower portion of the atmosphere. In the present session, we discuss about space waves, we discuss about troposphere nature, and also we discuss about the interaction between the two, space waves and troposphere. We begin the session by considering three major modes of wave propagation briefly. What are the three major modes? Ground wave. Wave assumes this mode, ground wave mode, when its frequency is below HF. Sky wave, when frequency of the wave is within HF band, then the wave assumes sky wave. When frequency is above HF band, wave assumes the mode of space wave. Diffraction plays an important role in ground wave propagation. Refraction plays major role in sky wave propagation, whereas reflection plays a role in the functioning of space wave communication link. All the three modes of wave propagation, they are illustrated here. Sky wave is shown. Notice the transmitting antenna, it is looking towards upper portions of the atmosphere. It emits a wave. This wave then travels towards ionosphere, which is upper portion of the atmosphere. There it gets refracted back towards the earth like this. When we place an antenna, receiving antenna, in the path of the wave that is coming back towards the earth, it can be received by the antenna and processed by the receiver equipment to get back the original signal. For successful operation of a sky wave link, one or two aspects or conditions are to be satisfied. One is frequency of the wave should be in HF band. The antennas must be looking towards ionosphere, upper portions of the atmosphere. This is another condition. Now ground wave propagation, ground wave communication link. When antennas are located near to the surface of the earth like this, and when the transmitting antenna is emitting a wave whose frequency is below HF, then the wave simply drops down to earth and it starts traveling over the surface of the earth towards the receiving antenna. While traveling over the surface of the earth, it undergoes phenomena diffraction. Diffraction helps in carrying the signal from transmitting antenna to receiving antenna when frequency of the wave is below HF. Here, ground wave is shown as a surface wave. It is named as a surface wave. Now we move to third mode of wave propagation, space wave. Here is shown two waves, direct wave, reflected wave. These two are part of space wave link. Direct wave straight away travels and reaches the receiving antenna, whereas the reflected wave hits the ground surface, gets reflected from it, and then reaches the receiving antenna. The signal at the receiving antenna is therefore vector sum of signal strength due to direct wave plus signal strength due to reflected wave. We are going to see the presence of reflected wave is unwanted, undesired, as it reduces the signal strength at the receiving antenna. In case of space wave link, both the antennas are located in troposphere and both the waves, direct wave as well as reflected wave, they exist in troposphere. Hence, space wave links are sometimes called tropospheric communication links. In the present session, the focus is on space waves, troposphere, and the interaction between the two. Now, a small introduction to space waves. The space waves, also known as tropospheric waves, are made up of waves that travel the direct path from the transmitter to receiver and ground reflected wave, which is a signal arriving at the receiver after being reflected from the surface of the earth. So space waves are also known as tropospheric waves. Space waves consist of two parts, two components. One component is called direct wave, another one is called reflected wave. The signal strength at the receiving antenna is also contributed by a component which includes that portion of energy received as a result of diffraction around the Earth's surface and refraction in the upper portions of the atmosphere. The diffraction component is considerable only when antenna is located near the surface of the Earth. Actually, this diffraction component is ground wave, but it can affect space wavelength only when antenna is located near the surface of the Earth. Usually, in space wavelength, antennas are located at a height from the surface of the Earth. So this part can be neglected. The space wave proper predominates when antenna is located at a larger distance from surface of the Earth, which is usually the case. Introduction continues. Line of sight, or LOS in short. Conditions must prevail in between transmitting and receiving antenna of a space wave communication system. What is line of sight, LOS in short? If antennas are able to see each other, then we say line of sight conditions are prevailing between the antennas. If there is an obstruction between the antennas preventing one antenna seeing the other, then we say line of sight conditions, they are not prevailing, existing between the antennas. For satisfactory functioning of a space wave link, line of sight conditions must be there. As the wave travels in straight line, they travel almost like uniform plane waves in straight lines. So space waves travel as uniform plane waves in straight lines. The transmitter and receiver of the space wave link are located in the lower part of the atmosphere. This lower part is called, as already mentioned, troposphere. The properties of this part of the atmosphere change with height. The modeling of the troposphere is required so that its impact on the traveling wave is assessed easily. So medium in which space waves travel is troposphere. Medium affects wave propagation, waves traveling through it. To assess to what extent wave propagation gets affected by the medium, we need to model that medium. In the present case, the medium is troposphere. The atmospheric density is highest near the Earth's surface and it monotonically decreases with altitude. This is one important property of the troposphere. Density is highest near the surface, it decreases with increase in height. Free space propagation. At the receiver of link, the signal consists of direct ray and ground reflected one. This fact has already been mentioned, illustrated in the beginning of the session. The signal strength at the receiver due to direct wave can be estimated with Friis formula. As already mentioned, signal strength at the receiver is vector sum of two waves, direct wave, reflected wave. Here it is mentioned that signal strength at the receiver due to direct wave. We discuss about signal strength due to reflected wave later. Right now it is signal strength due to direct wave. It can be estimated with the help of a formula, a popular standard formula, Friis transmission formula. The free space transmission of wave is characterized by straight line path and communication link which is based on straight line wave path is called line of sight link or space wave link. What here is being told is in free space wave travels in straight lines. Space waves in troposphere also travels almost in straight lines. So space wave link is almost like a free space wave link. Why this connection between space wave link and free space transmission wavelength is given here? Reason is Friis formula. It has been derived for free space transmission of wave. As it is applicable to free space transmission and space wave transmission or propagation is similar to, almost same as free space transmission of wave, we can use Friis transmission formula to estimate the signal strength at the receiver of a space wave link. The power received PR by an antenna located at a distance is given by this formula. This formula is Friis formula, Friis transmission formula. PR is equal to PT, GT, GR, lambda square over 4 pi R whole square. What is PR? P stands for power, R stands for power received by the receiving antenna. PT, power transmitted by the transmitting antenna. GT, gain of the transmitting antenna. GR, gain of the receiving antenna. Lambda, wavelength corresponding to frequency of the wave. R is distance between transmitting and receiving antennas. So these are the meanings of symbols that are there in this particular formula. Now important features of space waves are given here. Space waves are also called tropospheric waves. Space wave propagation is also called tropospheric propagation. Mechanisms, it is free space propagation. A little bit of bending happens while the wave is traveling in a troposphere, but it is not at all considerable. Not only that, sometimes it is beneficial too. The bending is somewhat beneficial too. So major mechanism is free space propagation. Frequency, it must be above HF, therefore VHF, UHF, SHF. VHF means very high frequency, UHF stands for ultra high frequency, SHF stands for super high frequency. Type, line of sight communication, orientation of antennas towards each other. Range of terrestrial communication up to 50 kilometers. Polarization, usually linear polarization is used. Field strength at the receiving antenna is given by this formula. Square root of P eta naught GT over 4 pi multiplied by 1 over D. The meaning of all these terms, they are explained later. Applications, television, FM, radar, cellular mobile communications, etc. Microwave communication systems like radars, they employ space waves. Now, a few points regarding troposphere. The properties, characteristics of a troposphere. As already mentioned, troposphere is lower portions of the atmosphere. The wave travels in the troposphere. Antennas are located in the troposphere. Entire space wave communication link is in troposphere, lower portions of the atmosphere. Regarding these lower portions, a few points are given which describe the nature of the atmosphere. Standard dry atmosphere. It is one in which temperature decreases at a rate of 6.5 degrees centigrade per kilometer. Standard dry atmosphere. Standard moist atmosphere. It is one where water vapor pressure is 10 millibars at sea level, decreasing with altitude at the rate of 1 millibar per 1000 feet up to 10,000 feet. So dry atmosphere, moist atmosphere. Standard dry atmosphere, standard moist atmosphere. Now standard propagation. It takes place in standard atmosphere, and if the temperature or water content differs from standard conditions, then non-standard propagation takes place. So if wave propagates in standard atmosphere, then it is standard propagation. If it propagates in not standard atmosphere, then it is non-standard propagation. Here it is appropriate to include is one for which. Now another point, the index of refraction is approximately 1.0003 at Earth's surface, but decreases to unity at great heights where the air density approaches to unity. Continuation. Here some points regarding standard atmosphere. A change in the refractive index with height causes a ray traveling in the atmosphere to bend away from the regions of low refractive index towards regions of large refractive index in accordance with Snell's law. So what happens is, this is Earth, refractive index decreases, n decreases with increase in height. So wave bends towards regions of large refractive index. It means a wave traveling like this, it bends like this. We are going to see this bending is beneficial as it enhances the link range. When it comes to the bending of the waves, it is the gradient of the refractive index that matters most. The relation between the wave path curvature radius rho and the change of refractive index or dielectric constant epsilon r with height h can be found as rho is equal to minus 2 over d epsilon r by dh. The height is sometimes indicated by capital H, sometimes by small h. Anyway, h is, whether it is capital H or small h, it is height above the ground. This is the relation between rho, curvature radius of wave path, and change of refractive index or dielectric constant with height. We introduce another parameter, modified refractive index. We know something about refractive index. It is modified so that modeling of the troposphere becomes easy. Space wave paths become more traceable, easily traceable. For that purpose, refractive index has been modified. Resultant one is called modified refractive index. It is customary in radio wave propagation work to use modified refractive index denoted by capital M. It is related to ordinary refractive index n through the relation m is equal to n minus 1 plus h over a multiplied by 10 power 6. From the expression, this expression, it can be noticed that modified one m is ordinary refractive index n modified to take into account the curvature of Earth. The quantity n minus 1 is called refractivity. Here is n minus 1. This part is called refractivity, and factor 10 power 6 is included to reflect even small variations in the refractive index. The aspect of M that is most important in describing the wave propagation is its variation with height, dm by dh. Already we have seen curvature radius of the wave depends upon variation of refractive index with height. Modified refractive index is ordinary refractive index with modification. Hence, we can conclude, we can understand very easily that variation of modified refractive index with height plays an important role in describing the space wave paths. Some more points regarding modified refractive index. In the standard atmosphere near the surface of the earth, the ordinary index n decreases with the height, but modified refractive index m increases linearly at a constant rate of 0.036 feet. At higher altitudes, the index n becomes independent of height, and the modified index m increases at a rate of 0.048 feet per foot. However, when air masses differing in temperature and moisture content overlay on each other, the corresponding m curves no longer have linear variation with height. It leads to formation of ducts, which are described later in the coming session. The primary benefit of a modified refractive index m lies in the fact that its usage in analysis of ray paths simplifies computations when rays under consideration are of different curvatures. When the decrease in the refractive index with height is at such a rate that m remains unchanged with height, then curvature of the ray is the same as that of the earth. On the other hand, if the refractive index of the atmosphere increases with height, the ray path will be bent away from the earth. With the use of m, the straight rays above the curved earth come out as curved rays with an upward curvature above a flat earth. When conditions correspond to standard atmosphere, the wave path will be bent, refracted slightly in contrast with the straight line path, which corresponds to refractive index that does not change with height. The curves that show variation of m with height are called m curves. From these curves, it is possible to predict the transmission path at least roughly. Depending upon the shape of these curves, different types of propagation can be defined. So what is the point here? Space waves are supposed to travel in straight lines, but under the impact of index change with the height in the troposphere, the wave paths are not truly straight lines. The paths get bent, and for satisfactory functioning of the link, we have to place the receiving antenna in the path of the incoming wave. So we need to know the path of the incoming wave so that we can place the receiving antenna at the appropriate location or point. Then how to find the path of the wave? Modified refractive index is useful. The curves which show variation of m with height, called m curves, they are useful. Now some more points regarding types of propagation. Standard propagation, this term has already been encountered earlier in the present session. Here we understand it with respect to m, modified refractive index. Standard propagation. If m increases linearly with height, m curve is straight line with a positive slope, and standard propagation takes place. Substandard propagation. If the slope of the m curve decreases near the surface of the earth, the rays curve upwards over the flat earth more than for normal conditions, resulting in substandard propagation. Superstandard propagation. If the slope of the m curve increases near the surface of the earth, the upward curvature of the rays is less, achieving greater coverage. In this case, superstandard propagation takes place. So here, standard propagation, substandard propagation, superstandard propagation, three terms are described. The description is with respect to M curves. If the M curve becomes vertical, that is no change of modified index with height, the rays over the flat earth are straight and a very great coverage can be obtained. This situation occurs when actual rays have the curvature same as that of the earth. So if the curve is vertical, M curve is vertical, range becomes large. We move to another parameter, effective radius of earth. We know ordinary radius of earth. Here the parameter under consideration is effective radius of earth. In studying the behavior of space wave under conditions of different refractive index gradients, it is often convenient to change the coordinates in such a manner that the particular path of interest becomes a straight line instead of a curve. This requires that radius of curvature of earth be readjusted to preserve the exact relative relation. In addition, to make the straight line path equivalent to curved path of the ray, it is necessary that change in height dh of the ray to be the same for same horizontal distance d in two cases. Sometimes capital H is indicated by small h2, capital D by small d2. In this process, to compensate for the curvature of the wave rho, a larger value of radius for earth known as effective radius or effective is considered instead of actual radius A in the computations. This effective radius actually depends upon the radius of curvature of the wave and the true radius of the earth. It is given by this formula. R effective is given by 1 over 1 minus A over rho. Rho is curvature of the wave, radius of curvature. A is radius of earth, actual radius. This expression 1 over 1 minus A by rho gives effective radius of earth. It can also be expressed as product of a constant K and true radius of earth. R effective is K into A. For standard atmosphere, the radius of curvature of wave is equal to 4 times the actual radius A of earth, and then the constant K becomes 4 by 3. The constant K can also be expressed in terms of gradient of modified refractive index in the following way. K can be related to modified refractive index. The relation is K is equal to 0.048 over dm by dh. Here dm by dh is change in m with respect to height. For standard atmosphere, the gradient dm by dh is equal to 0.036, resulting in same value for the multiplying constant K, that is 4 over 3. When dm by dh is 0, the equivalent radius of earth becomes infinity. That is, rays behave as though they traveled in a straight line over a flat earth. In the computation of the space wave paths, the usage of effective radius instead of actual radius makes the paths straight, and the bending of the waves in the atmosphere can be accounted for systematically. With this, we come to an end to the present session, which is first part on space waves. In this session, the focus has been on space waves, troposphere, and the interaction between them. Modified refractive index, effective radius of earth, phase transmission formula. These are some of the aspects, some of the quantities and relations that we encountered during the discussion. Hope this session is useful to you. We meet soon in a session on space waves second part.